Okay, it is my great pleasure to introduce my friend and colleague and long-term collaborator from the University of Warsaw, Piotr Mikołaj Sołtan. Piotr was born in May 2003 as a mathematician. He got his PhD from the University of Warsaw under the supervision of our superstar Professor Woronowicz. But he got his habilitation at IMPAN. I still remember voting yes for awarding him this degree. And he became a full professor in 2021. He had numerous awards from the University of Warsaw. The list was kind of uncountable, if I might say so. And even served for 1 year as the head of a department of mathematical methods in physics. He is internationally recognized top expert in quantum groups, especially functional analytics 9. He brought up 2 PhD students who graduated under his supervision. And if I might add, he is an absolutely superb lecturer. So please buckle up and enjoy the ride. The floor is yours. Take it over.
Thank you very much. Now I'm under pressure in terms of expectations, but thank you for letting me present this talk for young people. Okay, I will just need to organize myself. Okay, this doesn't work. Oh. It is on. It is. Well,
what do I do with this one?
Okay. Oh, now it works. Okay, good. All right. So this is the plan of my talk. Okay, it's impossible to look up there, so I'll be looking down here. Sorry. My plan is to not necessarily give you all the detailed definitions, though they will come at some point, but mainly to motivate the study of quantum groups with basically 1.5 specific example. And we will start with classical groups, so everything will be very easy at first. We'll sort of accelerate towards the end. And at the very end, we will actually discuss one very new thing and an open question, or maybe a couple of open questions. Let's begin. We start with the group SU2. So SU2 is a group of unitary 2x2 matrices with determinant 1. Of course, there are matrices with complex entries, because I'm speaking about unitarity here, so that's sort of obvious. And it is a very important group for many reasons. From the point of view of theory of Lie groups, it's a fundamental somehow building block, especially the Lie algebra, this algebra for all semi-simple Lie groups. So, but it's also very important in physics, responsible for the spin and also isospin in particle physics. So this is something that needs a lot of attention. And and I will actually comment on this a little bit more later. So we have this group, and it's very easy to convince oneself that all elements of this group are matrices of this form, where A and C are complex numbers that satisfy this equality. This is a next to trivial exercise, so we leave it, and we also note that if you write these two complex numbers A and C as split into their real and imaginary parts, then this condition simply means that x1 squared plus x2 squared plus x3 squared plus x4 squared equals 1, which is exactly the equation defining the 3-sphere in 4 dimensions. So that means that as a set and as a topological space, and in fact as a differential manifold, SU2 is just a 3-sphere, so it's a very nice differential manifold. Okay, and also the group operations. Well, here the one is the multiplication of matrices written out for matrices of this form. This is what you get when you multiply 2 of them, and also taking the inverse. This is taking the inverse of a matrix, again, for matrices of this particular form, they are continuous functions. In fact, they are smooth functions. So that means that SU2 is a Lie group. But we will not, in fact, be going very deep into this fact. The fact that it's a Lie group is less important for us than that it's a topological group. So it's a group with a topology, and group operations are continuous. Okay, so now this here is quite a big fact summarized in the phrase "it is known that," but I'm guessing I could convince you maybe in a couple of minutes, I guess, but that to talk about a compact space is exactly equivalent to talking about the algebra of all continuous functions on this space. The algebra remembers everything about the space. This is more than just an algebra, and it's a Banach algebra, meaning it's a Banach space, and it's also a star algebra. And here is the explanation of the structure. So the algebra structure, the multiplication structure, is just pointwise multiplication of functions. This is the standard way you multiply functions. The norm is the supremum norm standard in this story, and the involution is just taking the complex conjugate of a function. And this way, on the set of all continuous functions on SU2, we obtain a structure of a Banach star algebra. In fact, it's a unital algebra because the function which is constant equal to 1 is the unit of this algebra. And as I said, this algebra remembers absolutely everything about the space. Our next goal is to see how the fact that this space is a group is reflected in this algebra. This point is just a summary of what I just said. And let's, before going further, let's also define two special elements of our algebra. I will call them alpha and gamma. They are the functions that assign to a matrix. Well, alpha assigns the upper left corner, so the matrix is mapped to A, and gamma assigns the lower left corner, so this whole matrix is mapped to C. These are clearly continuous functions on the group, so they belong to the algebra of continuous functions, which we want to study. And then we can take these two functions and use the operations of pointwise multiplication and involution, and of course addition and multiplying by scalars to generate the subalgebra that contains these two elements and is formed, in fact, of all polynomials in alpha, gamma, and their images under the involution, which will be denoted by alpha star. I don't think I put this definition anywhere, but we're talking about a star algebra which has this involution, but we will drop the notation of a bar. We will just write a star as for the complex conjugate function, because later on we will deal with algebras with involution without that interpretation. This algebra of these polynomials in alpha and gamma, and alpha star and gamma star, they form a nice star subalgebra. In fact, this algebra is unital. The subalgebra is unital because the unit of our algebra, which is the function which is constant equal to 1, is expressible exactly like this. Why? Because alpha star is the function that assigns to a matrix like this the conjugate of A. Alpha assigns A, so alpha star alpha assigns modulus A squared. And similarly, gamma star gamma assigns to this matrix modulus C squared, and this is exactly the equation that we looked at. Alpha modulus alpha squared plus modulus gamma, modulus A squared plus modulus C squared equals 1, and this is this. Okay, so we're getting used to looking at so-called commutation relations between elements of an algebra. Okay, and the final thing is that by the Stone-Weierstrass theorem, this star subalgebra is dense in the algebra of all continuous functions on SU2. This is again a standard result. So this way we found that our algebra of functions on continuous functions on SU2 has these special two elements which generate a dense subalgebra in all continuous functions, and topologically they just generate C of SU2. Okay. So now let's look at how the fact that our space SU2 is equipped with multiplication, how it is reflected in the algebra of continuous functions. Well, if you take a continuous function f, you can make out of it a new function delta of f, which will be a function of two variables from SU2, and this is the definition. So delta of f evaluated at a pair of matrices A and B is f applied to the product AB. So, oh, this is supposed to be small f, sorry. I was holding the shift for A and B and the fact of that. Well, it's sort of spoiled a little bit, but this is how you transfer the structure of multiplication from the space to the set of functions. Okay. Thing is that you can write an equality like this. It is, the left-hand side it's clear what it is. This is a continuous functions of two variables on SU2. The right-hand side, well, I mean, you can take this vector space, take the vector space tensor product with itself, and then it's not exactly true that this equality holds. You need to complete this normed space in a certain norm to make it a Banach space, and then the completion, so the completed tensor product in an appropriate sense, gives you the exact equality here, with norm equal on both sides.
The question?
Yes?
So it's relevant in which C-star norm?
In this case, there is only one C-star norm. This is one of those cases, because this is a commutative algebra. Yes, which follows from commutativity. Yes. In general, there are many different norms in which we complete, but here it's there is a unique C-star norm. Okay, we will come back to C-star algebras later. Anyway, our delta, which was mapping functions of one variable to functions of two variables, now is a map from this Banach space to this Banach space, which is the tensor square in an appropriate Banach space sense. Okay, and it's easy to see, really simple exercise, that delta preserves all the structure. It's a linear map which is multiplicative, which is compatible with taking complex conjugates, so this involution star, and also it's, in this case, it's isometric. It's the nicest Banach space map. Moreover, associativity of multiplication, which we know we have for groups, so in SU2, leads to this equality, which is called co-associativity. We're not going to go into details of why this is true, but this is just translating associativity to this new, let's say, point of view. And also one other thing, we call this map delta co-multiplication. It's co-multiplication because it's dual to multiplication. Okay, so continuing this, here is again the formula for multiplication of matrices. So we have A, we have B, and this is the product in SU2, so they are all of this special form. And it follows from this formula immediately, really, that we can write very nice formulas for delta of alpha and delta of gamma. Look, what is delta of alpha? This is the function that returns, given two matrices, the upper left-hand corner of the product. Okay, so it is supposed to return this. So it will be the upper left-hand corner of the first one times the upper left-hand corner of the second one. That's this. Minus the conjugate of the upper right-hand corner of the first one. Of this. I mean, it's easier to see. The minus conjugate of this C times this C prime. And this is exactly here. This is the minus. This star is this conjugation here. And, well, you see it. I mean, basically explaining it is worse than just showing the formula. So similarly, this is the formula for delta of gamma. So we have nice formulas for what this delta does to our generators, our special functions that we like on our. Moreover, we can look at this matrix of functions. This is now a matrix of functions, or in other words, a matrix valued function on our group. This is, so we call it U, and then U is an element of 2x2 matrices over functions on SU2, but 2x2 matrices over functions on SU2 is exactly the same. Now here, because matrices are finite dimensional, this tensor product is just the algebraic tensor product of vector spaces and this natural isomorphism of vector spaces and algebras. And this algebra of matrices over an algebra with involution is again an algebra with involution, because you can take, like you take permission conjugation on matrices, but instead of complex conjugation, you put a star over elements of the matrix. So you take a transpose and put a star everywhere. And this is a star algebra, and then it makes sense to call something a unitary. Unitary element is an element whose adjoint is its inverse. Okay. And also there is this formula for co-multiplication on all elements of this matrix. On alpha and gamma, we already have it up here, but I wanted to put this formula up here because, well, it should remind you of a multiplication of matrices. The only difference is the tensor product symbol here instead of just multiplication like for scalar matrices. Okay, and this is a formula with a name. Okay, so now, so far we only looked at SU2 and we looked at multiplication. There was a point where I mentioned taking inverses, but I didn't really transfer taking inverse to the level of the algebra. I could do that, but instead, for reasons of the theory of compact quantum groups, which is far off in the future now, well, not far off, within half an hour, we'll get there. We want to encode the fact that every element is invertible in a different way than just writing it out that every element is invertible. This is the way to encode it. It's not obvious that it's equivalent, but it is equivalent here due to compactness of SU2. I will not go into details. You'll just have to believe me that the fact that every element of our so far semi-group SU2 is invertible is equivalent to the fact that these two cancellation laws hold. So you can cancel out a matrix as if you knew it was invertible and then you do it, right? But this is the fact that you can cancel is equivalent to the fact that they are all invertible. Okay, and now these things, these two laws, have a nice expression in terms of this algebra and continuous functions on SU2 and this co-multiplication delta. It's well, again, this is not obvious, but it's along the lines of Stone-Weierstrass theorem and things like that. So what are we looking at here? We are looking at a set of functions of this form, functions of two variables. What are these functions? You take a function of one variable and you make it into a function of two variables with delta. And then you take another function of one variable and, well, you tensor it by one. So you make it a function of two variables, but it only depends on the second one. So one tensor G evaluated in A comma B is just G of B. Doesn't care about B. And then you multiply such functions of two variables, and you take linear span. And then it turns out it's dense in the density of this set in the tensor product CSU2 tensor CSU2 is exactly this long. And similarly here, the difference is that here G was on the right and here F is on the right. And this is. So we were able to write the fact that SU2 is a group in a completely different way. As I wrote here, counterintuitive in a way, but it only involves delta, it only involves SU2, and this is sort of important for later, it doesn't involve taking any special matrix and saying there exists a universe. This is, we want to avoid looking at points. We want to write everything just by functions, not looking at points of our space. Okay, so let me show you a sort of a sketch of an argument why this is dense. We already know, I told you it was equivalent to one of these cancellation laws, but say we don't know this and we want to check that it's dense. So let's look at this unitary matrix again. This is a 2 by 2 matrix of functions on SU2, which is an element of matrices tensor functions. The equation star, which was the equation that said what delta does to all matrix elements of this matrix, all 4 of them, it's equivalent to this, and I will in a second explain what this is, but I want to caution you here. U12 looks very much like a 1-2 element of your matrix. It is not. Whenever I write elements of a matrix, like here, where was this star here? There is a comma between the indices. And here, okay? It is not present here, so that is just notation for this. And this is notation for this. So what is it? Well, I have a formal, do I have a, no, I don't have a formal definition here. It will come later. So we just make a matrix of functions of 2 variables, but they don't care about the second variable. This is this matrix, but sort of tensor 1 in this, and U13 is this. So this is again this matrix, but instead of functions of 1 variable, we write them as functions of 2 variables, but they're constant with respect to first. So just this. And the thing is that if you take these 2 matrices and just multiply them, you get exactly what you would get by applying delta to every element in here. This is exactly this formula that we looked at, and I told you it resembles matrix multiplication. So it's exactly this. Okay, so we have this. In particular, we can multiply both sides by the inverse of U13 from the right. But U13 is a unitary matrix. Its inverse doesn't involve taking -1 of anything. It only involves taking the involution, applying the involution, which means taking a transpose and putting star everywhere. So U12, so this matrix, is this matrix times this little one here. Just the product of 2 matrices. Now look, this first one is U with delta applied to every element. And U13 always has 1 on the left leg, as we call it. So this, let me maybe jump back. Oh no, I don't need to jump back. I actually have it right here. This is a matrix of elements of exactly this form. Because it's always delta of something in this matrix times elements of the form 1 tensor something. So this is exactly here. So all matrix elements of this lie in here. And if they lie in here, you can always multiply them by anything, like by any 1 tensor anything again, because it's invariant under this fact. This means that all these matrix elements belong here, and you can, by multiplying again with one tensor f, you get alpha tensor anything, and gamma tensor anything, and gamma star tensor anything, and alpha star tensor anything. All of these elements belong here. Okay, so, well, it's not exactly the proof that these elements are dense, but at least we showed that a lot of things belong to this set. And now the next step is, instead of our matrix U, take this matrix, which I call the tensor product, and it also looks like a tensor product of matrices. So why is it? Well, it's like, look, this here, it's just alpha times every element of the matrix U. This thing here is gamma times every element of matrix U. This is alpha star, and this is minus gamma star, again, times every element of the matrix U. This matrix is again unitary, and you can play the same game because it also behaves identically under delta. And now this matrix has degree 2 polynomials in alpha and gamma, all possible monomials, in fact, in here. And using exactly the same reasoning as before, you can get any degree 2 monomial, tensor anything else, all belonging here. And you just iterate this procedure, and you get absolutely any polynomial in alpha and gamma, tensor anything belonging to this set. And this we know is dense because polynomials in alpha and gamma and alpha and gamma star are dense. So this is a way to show that, in fact, our density condition is satisfied. Well, you do the same thing for the other density condition, and then, as I said, you have to do a little bit of magic to show that this is equivalent to the fact that every element of SU2 is inverted. Okay. Linearly dense every time, yes. Yeah, I guess I wrote this before, but I kept saying just dense. Okay, now we get to a question which occurred to people, I guess, in the early 80s. Can we deform this structure? Why do we even care about deforming the structure of a group? Well, this has some motivation in physics. You see, for example, the symmetry group of relativistic physics, which is the Lorentz and Poincaré groups, they have a parameter, which is the speed of light. And in a way, if you go with this parameter to infinity, you obtain symmetry group of a different theory. That somehow motivates this question, well, if SU2 is the symmetry group of so much phenomena of physics, maybe there is this is just a limiting case of some other symmetry which we didn't know about. Is there some other group which is really close and maybe describes somehow symmetries of slightly different physical theory? Well, so here this question is written using phrases like "in some sense." Well, because you can probably deform things in many different ways, approach this question in different categories, and so on. One way to do this, I don't want to go into details on this, but you can say, okay, let's recall that SU2 is a Lie group. You can choose the basis in the Lie algebra, and then you have structure constants, which just tell you what the brackets of the basis vectors are expressed in the basis, and look at all compact Lie groups that have very close structure constants for some choice of bases in their Lie algebra. But the thing is that actually doesn't work. There is a certain rigidity of semi-simple compact Lie groups that says that if something is really close to SU2, it's really isomorphic to SU2. So there is no deformation procedure in that sense. So let's see if we can deform our group in some other way. And I guess maybe we could say in a different direction. So this different direction is, let me maybe, let's recall that continuous functions on the compact group SU2 is exactly the Banach-Star algebra generated by two elements, alpha and gamma, with this relation. And also, all of these things commute because they are functions on a space. So, of course, their multiplication is commutative. Also, there is this fact, and here we are getting into the story of C-star algebras, that there is a relationship between the norm and the involution and multiplication in this algebra. It's a very special relationship. This is a famous C-star identity. So we call this the C-star algebra. In other words, continuous functions in SU2 is the C-star algebra generated by two elements which commute, and all of their adjoints commute with everything, and with this relation. Now, consider a real number between -1 and 1, not equal to 1, and for other reasons that I might go into later, not equal to 0. And consider the C-star algebra generated by some elements alpha and gamma. This is now completely abstract, no longer connected to the group SU2 itself, that satisfy these relations. So this first relation is, of course, exactly the same one as here. Where are the differences? Well, the difference is here. Alpha gamma is not equal to gamma alpha, so our two generators will no longer be commuting. The difference is very slight. The difference is just that alpha gamma equals q gamma alpha. And there is another place where you need to insert q for everything to make sense. So, well, this relation, well, basically, this says that alpha star alpha is not equal to alpha alpha star. They differ by 1 minus q squared gamma star. 1 minus that. Okay. So, okay, so this is just a proposal. Let's generate an algebra, a C-star algebra. There is a way to do this. Of course, we will not be getting into details of this technical problem of generating a C-star algebra. And we just give it a funny name, continuous functions on SUQ2. Now, C of SUQ2 defined above is not commutative. This means that this is just notation. There does not exist space such that this would hold. It's just a notation for this non-commutative C-star algebra. Okay, here's a theorem. This non-commutative C-star algebra admits a map, a unital star homomorphism, which behaves like this on generators, which is almost exactly the formula, the two formulas we had for delta of alpha and delta of gamma when we were talking about functions on SU2. This co-multiplication is co-associative. And these sets can be shown to be linearly dense in the tensor product of this algebra with itself. So what we did is we took a commutative C-star algebra of functions on a compact group. We looked at it, found generators and a presentation, a nice relation, alpha star alpha plus gamma star gamma equals 1. We introduced a Q, which changed this presentation, made it a non-commutative algebra. But everything that we liked about the previous algebra is still there.
And that puts the deformation in. Yes, you cannot play with. You cannot play with where to put.
Oh yeah. There is just one way to do it.
Okay.
Yes. Yes. Of course. Yes.
The other way around.
Yes. Yeah. You can do this for any complex system. There is a way to do it, but it takes a long time to explain. Anyway, what we just defined is. Yeah.
But it's not the same. The same is not true about higher dimensions. Okay. with lower dimension. Okay, but indeed, it needs only
As you
one unique deformation in the realm of sister algebra. But if you go to SUN, you have this wonderful paper born out in the Sonnet, we have a plethora of different deformations. SUNs.
Well, but only one of those you call quantum SUNs for reasons of representation theory. So you can deform the C-star algebra, yes, but if you want to have a deformation of SUN, it's still unique. It's the Drinfeld Jimbo. Anyway, it's
Like you need some further.
yes, yeah, okay. Okay, so what we just defined is a compact quantum group. We had a compact group, SU2, and what we did was we took functions on it, deformed it, but it turned out that it still has a co-multiplication, it's co-associative, it has these density conditions, and we call this, whatever it is, a quantum group. There is no object like this. I mean, the object is described by the C-star algebra with a co-multiplication, but we sort of use the language of saying it's functions on a quantum group. It's not functions on anything. It's just a language game.
So it breaks this duality. It means that this C-star algebra is not the algebra corresponding to any topological space via this duality, yes, but still breaking this duality, you can assign some topological space in spectrum or something.
Oh yes. Well, this duality holds the category of compact spaces is the dual category of the category of commutative unital C-star algebras. So if we got out of commutative, in a way we got out of compact spaces. We got into compact quantum spaces. That's the philosophy of it, I guess. Okay, let's continue because I'm actually running late. All right. So what else do we do with groups, with topological groups, especially compact ones? Then everything is easy. We have the Haar measure on compact groups, on all locally compact groups, but compact groups in particular, we have the normalized Haar measure, and therefore we can integrate functions. So we have this functional, which takes a function and assigns to it the integral. For continuous functions, it's well defined, right? Take integrable functions, but we are dealing with continuous here. And this is a positive functional of norm 1. Positive means takes positive functions. A positive functional of norm 1 in the lingo of C-star algebras is called a state, because it's like assigning a value to an observable in a state. But so we use the word state for such a thing. And this here is the way we can express the fact that our Haar measure is the Haar measure. So it's the measure which is invariant under multiplications. You see, here you take a function f, you apply it to two variables, let's say a, b, and then you integrate with respect to the Haar measure along a, the first variable. And this equality says that the resulting function is constant, doesn't depend on b. So this is exactly the right invariance of the Haar measure. And this equality is the left invariance of the Haar measure. So the Haar measure is a state, a linear positive functional of norm 1 on our algebra, which has these properties here. Here we have the analog for the quantum. There exists a unique state H on this C-star algebra, this non-commutative C-star algebra, which satisfies exactly the same things as here. Right? So the remark is for just a compact group. The theorem is for this quantum group that we defined. In fact, well, here's the name for this function, the Haar measure of a quantum group, and I can show you a formula for H. And this formula, I wanted to show you this because it reveals how we work really with these objects.
It's more like an integral with respect to the Haar measure.
Yeah. But in functional analysis, we basically identify measures with integrals. Yes. So let's look at a very nice Hilbert space. L2, I guess, sequences really because it's on a discrete set. L2 functions on z plus times z. So just Hilbert space with square integral functions with respect to the counting measure on this discrete set. And on this Hilbert space, we can first of all consider an orthonormal basis, which is just delta functions in points, right? Standard basis of this thing. And we can define two operators. This is supposed to be boldface alpha and boldface gamma. So we're just saying what these operators are doing on the basis. So just take a basis element and you get a different basis here. Similarly, the fact that n is in z plus, so it starts from 0, it might look strange because you're subtracting 1. What if n is equal to 0? You will get -1, but then you will get a 0 as this scalar, so you don't. So a non-defined element is multiplied by 0. So it's 0. Anyway, we have two concrete operators on a concrete Hilbert space. And now, here's the connection with quantum SU2, with SUQ2. There exists a unique star homomorphism that takes this algebra into operators on this space, such that alpha, one of the generators, is mapped to this operator, and the other generator is mapped into this. So our C-star algebra functions on SUQ2 gets mapped into operators on a Hilbert space. Oh, yes, of course. Uniqueness is a consequence of defining something on generators, so the whole thing is existent, of course. The funny thing is that we have a formula for the Haar measure. The Haar measure applied to an element, just any element here, say a polynomial in alpha and gamma or some limit of such. How do you do this? Well, you take this element. Oh, there is a mistake here. This here A, it's supposed to be pi of A. I guess I yeah. Okay. So you take this element, you map it to, it becomes an operator. It's an operator, you can act on a vector. You can take a scalar product with another vector. You can multiply it by a scalar. You can take a sum of these things. You get a number. And this number is this. Okay, so our study of particular examples on groups always happens in Hilbert space, basically. And this is why I talked about commutation relations, because this is what we study. This is how it's also quite similar to some problems in physics. Okay, I guess this pi of A here will disappear when I click this. So the last thing is that it's a fact that this pi is injective. So we really can consider our algebra C of SUQ2 as the algebra of these operators. It doesn't have to be so abstract and something. It can be quite concrete. It's two special operators which are defined here and all of their algebraic combinations and limits of those. Okay, so this was a slide to just explain this fact. And now let me quickly go through unitary representations. So what is a unitary representation of SUQ2? Well, it's a matrix of elements of CSUQ2. So of this non-commutative C-star algebra, which is unitary, and which, after applying delta to every element of this matrix, gives you U12 times U13, where it's exactly like it was for the 2x2 matrix at the very beginning. This is the definition, and the word flip means a tensor flip. Will come up later. Okay, so this condition here, it's equivalent to saying that when you apply delta to an element ij, here we have a comma. So this is an element of this matrix. matrix element number ij. The formula is just like matrix multiplication, but with a tensor product instead of just product. So if we have two unitary representations of SUQ2, we can talk about intertwining operators, and this is just like in standard representation theory. This is just algebra. What is an intertwiner of two matrices? Well, it's this. So this is exactly what it would mean if the group were classical, not quantum. Equivalence means that there is a unitary intertwiner. So we have the notion of equivalence of representations. We have the notion of an irreducible representation. A representation is irreducible when, well, classically we would say it doesn't have invariant subspaces other than 0 and the whole space. Here you can write it, it doesn't have self-intertwining projections, which are non-trivial, which is because a projection intertwining a representation with itself, so commuting with a representation, means that there is an invariant subspace. So we have irreducible representations. We have the notion of a direct sum of representations. Here is quite an obvious way to construct a direct sum of two representations. You get a bigger matrix. We have a notion of a tensor product of representations. I don't write tensor here. I write this funny T in a circle because this is not a tensor product of elements. It would be really confusing because if you have elements of some algebras, you take tensor products of these, then you think it's a element of the tensor product of algebras. It isn't. It is like this. You take U, which is an element in matrices tensor functions on SUQ2, and you stick a unit in the middle here. And you take the other representation, which is an element of matrices tensor C of SUQ2, and you stick a unit at the beginning. This 1, 3 means it lives in the first and third factor. 2, 3, it means it lives in the second and third factor, and in the remaining factor you put a unit. And well, here is the definition. I guess it's more easily explained by just sticking a unit in different places. So we have the whole setup of standard representation theory of in this case, compact groups, but it's for all groups. Yes. Yeah, it only acts on the Hilbert spaces Cn and Cn. Just like for groups, when you have representations of the same group on two different spaces, and you have a map between the spaces such that you can go from the group to an operator representing, and then by this operator, and it's the same as going through this representation. That's the intertwine. Yeah. The one lives in CSU. Yeah. So we have the whole setup of representation theory, and we can look at examples. So this one, the one we started with, it's a two-dimensional reducible representation of SUQ2. You can take its tensor square, which we looked at in the classical case at the beginning. And this is again a representation. It's not irreducible. It's equivalent to the direct sum of a trivial one-dimensional representation, which is just the unit of the algebra, which is like a 1-by-1 matrix of functions, plus this 3-by-3, so three-dimensional irreducible representation of SU2, which is, I mean, anyone who knows representation theory of SU2 will recognize that it's really analogous to the way things are for SU2. And in fact, we have a much better correspondence. The irreducible representations of SUQ2 up to equivalence are labeled by, well, one would call it spin, half integer positive numbers. And we can choose representatives so that the spin 0 is the trivial representation, spin 1/2 is the 2-by-2. And we have the standard decomposition of tensor products exactly like for SU2. And this can be proved for SUQ2 as well. So this is why we claim that what we defined is in fact a deformation of SUQ2. It's not just that we found a very nice presentation in terms of alpha and gamma and we stuck a Q in there and it looks similar, but in fact this object does behave like SU2, but it's not a group anymore, it's a quantum group. Okay, so this was, oh, by the way, so as I said, quantum groups can be defined like this for all compact semi-simple Lie groups, and the story is really long, but there is a completely different aspect to the theory of quantum groups, which is much more combinatorial. Namely, let me maybe do it quickly. Permutation matrices, everybody knows what permutation matrices are. The matrix of zeros and ones with 1 0 and 1 1 in every row. You can write it this way. And the symmetric group can be just thought of as this collection of all permutation matrices of a given size. It's the same thing. Now, consider the C-star algebra generated by n squared, so a squared matrix of elements, which form a square matrix, such that each of these elements is a projection. We call projection a self-adjoint idempotent, so something whose square is equal to itself and which is self-adjoint. And if you write this matrix, if you sum every row, you get 1. If you sum any column, you get 1. There is a nice terminology. This is called a magic unitary. Magic because you get the same in every row and in every column, and it's a unitary matrix. And the C-star algebra generated by such entries of a magic unitary is called C of Sn plus. C of Sn plus is a C-star algebra whose abelianization, which means what is abelianization? You look at this algebra and you add to this list of relations that say that all elements commute. If you ask that all these conditions are satisfied and all Uij's commute, you get a finite dimensional algebra of functions on the symmetric group. If you don't do this, you still have a nice co-multiplication on your C-star algebra, which has a very familiar form. It's co-associative, the density conditions are satisfied, and what we've defined is a quantum permutation group. This is called the quantum permutation group of n points. If n is equal to 1, 2, or 3, we actually get nothing new. It's exactly the same. It's just the algebra becomes the algebra of functions on on the trivial group on S2 and S3. But for n bigger or equal to 4, this C-star algebra is not only non-commutative, but it's infinite dimensional. In a way, there are infinitely many quantum permutations of 4 points. What is strange is that it's also compact in a sense. So you would expect that permutations should become discrete, but they're compact. It's a weird phenomenon, I would say. Anyway, so I don't. Yes.
Yes, I wanted to ask whether the definition of quantum group differ from the original permutation group.
Well, if you add the condition that all entries of your big matrix Uij commute, then you just get functions on the symmetric.
Okay.
And
we do not assume that for the neon.
No, you don't. No.
But we could still assume it. It's not like we're assuming that it does not commute, right?
Well, no, but we are looking at the algebra generated by such elements with such relations, so it's not commutative because it has non-commutative. It has non-commutative images. So,
yeah.
And okay, I'm going to skip this. It's easy to easy. It's well known what representation theory of this quantum group is, the Haar measure, everything is known about this. And it's just one of a whole ocean of different examples of quantum groups which are not of this deformation kind. They are sort of different. In fact, they're called, what are they called? Liberations.
Yeah.
You make them free. You don't make them commute. You let the generators be free.
Just can you remind me, beginning at which end is really going to be 3 or 4?
4.
4.
Yeah, 2 is on my semi groups that they already not the 2, but groups start at 4.
Okay, so after 3, you still get years of birth.
Yeah.
Then this sister routers grows very fast. Okay, then you can.
Okay, so here is something you could expect. What all that I was talking about is just a part of a bigger scheme. The compact quantum groups in general are described by C-star algebras, which are deceptively written as C of G, but they are not commutative. And this is why the G is a sort of a blackboard bold or something font. Equipped with co-multiplications, which are co-associative, neutral star homomorphisms, and such that these density conditions hold. And well, we had 2 examples so far, apart from all classical compact groups also giving such examples, like SU2. We had the SUQ2 example and the SM plug, so the liberation of the permutation group. And in the 80s, Voronovich proved that in all such cases you have Haar measure. And the Haar measure is crucial for a lot of things. So this is how you start the theory when you have such a really great tool. Well, in particular, with you can have other examples. So you can take any discrete group, you can take the left regular representation of this group, which is just representation on L2 of the group by shifts. So this is the formula for the left regular representation. You look at the algebra generated by these operators inside B of L2 of gamma, and you give it a funny name, C of gamma hat. And this actually has a co-multiplication like this, which is uniquely defined by acting on these operators lambda of S. They produce lambda of S tensor lambda of S. This is a co-multiplication. It's co-associative. The density conditions are satisfied. So you get a compact quantum group, and you actually have the Haar measure. It's very well known, functional. This is called the von Neumann trace, which is you take an element of your algebra, you act on the delta function, so like a vector which is supported only on the unit. Well, then this operator just moves it somewhere, and you take a scalar product with the original vector, and you get.
It should be lambda, yes?
Well, not anymore, because A is already a lambda of something. Here it's slightly different. I remember the problem in the previous slide, yes, but here A is lambda of S, for example. But if it's lambda of S, then it's usually 0. It's a polynomial in lambdas. Okay, the range of delta is contained in the space of symmetric tensors. It's because of this, clearly, every lambda is mapped to a symmetric tensor, and we say that we have a co-commutative quantum group. So every discrete group has a dual, which is a compact quantum group. Look, the group gamma is classical, completely standard notion of a group. The dual is already quantum, because this C-star algebra is usually non-commutative. I mean, it's only commutative if yeah. Okay, so the example of it is you take gamma, the integers, and your dual group is then the actual Pontryagin dual, the circle. So I write it T as a one-dimensional torus. Yeah, but there were questions, so 5 minutes. All right, let me see. Yeah, I know, I should have been right. Okay, instead of describing what's on this set, I will just try to dazzle you with this. There is the world of locally compact groups, which are objects with, well, they can be compact quantum groups like we defined, but they are similar kind of thing, but the C-star algebra that describes them is not required to be unitary. So we are thinking of the real line can be described with the algebra functions that vanish at infinity. It doesn't have the unit because the unit doesn't vanish at infinity. And the difference between compactness and non-compactness is really in whether this algebra is unitary or not. In this world of locally compact quantum groups, you can include all locally compact groups, compact ones, discrete ones, all of them. In particular, you can look at abelian locally compact groups, which have Pontryagin duality. So the dual of R is R, the dual of Z is T, and so on. This Pontryagin duality extends to all locally compact quantum groups. Every quantum group has a dual. In particular, every locally compact group has a dual, only sometimes it's not a group, it's a quantum. Duals of compact quantum groups are discrete quantum groups, and in a way, they are two sides of the same coin. A compact group has the dual, which is discrete, its dual is back the same compact group, in particular, we can do the one last thing, so 2 minutes. I will just say here, GNS. So hopefully, at least some of you have heard about the GNS construction in C-star algebras. When you have a C-star algebra, like functions on a quantum group, and a state, like the Haar measure, you can create a Hilbert space and a representation of your C-star algebra from this pair, and it's exactly like the regular representation of a group, but in much bigger generality. And you can take the image of your representation, and you can take this strong closure, which is just take limits of all your operators, not only in norm but in strong topology. And then you get a von Neumann algebra, which is called L infinity of G. These L infinity of G algebras, this I have to skip because I was going to give you a proof of something that takes way too long. The ones that we are after are factors, so the ones which have trivial center, because pretty much like for matrix algebras, any matrix algebra is a direct sum of full matrix algebras, right? Any finite dimensional, whether it's like the Wedderburn theorem, right? Any finite dimensional algebra over C is a direct sum of semi-simple algebra over C is direct sum of full matrix algebras. So full matrix algebras have infinite dimensional analogs called factors. And in case of groups, the group algebra has trivial center in this sense, if and only if your group is so-called ICC, so infinite conjugacy classes. All non-trivial conjugacy classes in the group are infinite. And the recent developments in this story are that we are looking for an ICC condition for quantum groups. And the starting point is that for classical groups, the ICC condition can be expressed using delta, which we described. And this prime here means commutant. So you look at the image of such a map, delta n, and you look at all elements in this tensor product which commute with the image of this map. If this is trivial, then we can call it NICC. And this is equivalent to just IPC there are more errors here. Anyway, sorry for rushing so much. There is the NICC condition for discrete quantum groups, and we have these questions. Which discrete quantum groups are NICC? We were able to prove it for some. Are all of these conditions with different ends equivalent? We don't know. What are other consequences apart from the fact that L infinity of G is a factor? We know some things about this, but it's still an open story. So sorry for taking it so far over time, and thank you for your attention.
Thank you so much.
Oh yeah, if you could do this, I would be very interested.
Can you say something about Polish spheres?
Oh yeah.
Also complication.
Oh yes. Yeah.
Let
So
me take right on this one because we will not see what.
oh, okay. All right. Very quickly. So the thing is that this quantum SUQ2 group has a subgroup. In an appropriate sense, you can define subgroups, which is just the one-dimensional torus. This is the standard. And there is a notion of taking the quotient. There is such a thing. It makes sense in the quantum group world as well. And this is one of the Podlesh spheres. This is one of the Podlesh spheres that he defined. Now, he found that for compact groups, it's well-known fact that homogeneous spaces is the same thing as ergodic actions. Here, a homogeneous space is one, but there are many ergodic actions which have exactly the same spectral decomposition. So basically, the family of Podlesh spheres is the family of compact quantum spaces with an action of SUQ2, such that it's the multiplicity of the three-dimensional representation, irreducible representation, is one in this space, just like it is for the classical sphere. And there is a whole continuous family of these spheres. This is what Piotr published did. This is very clever, and I happen to generalize this to so-called braided, which are quantum groups that have co-multiplications that have values in not a standard tensor product, but a braided tensor product where the factors don't converge. Okay.
This is a beautiful example of the whole thing.
Okay.
And actually, all these spheres of Podlesh are quotients. It's just that when you go beyond this standard quotient, you have to take the quotient in a very smart way. That's what we have.
Yeah, this is not the quotient that I understand.
Okay, any further questions?
I have a follow-up question. So, what is the right category in which you would like to see this for the sphere? So, it is no longer a quantum group, and as a sister algebra, it's just compacts. So,
no, it's well, it's not just compacts. This quotient one is the unitization of the
relation.
Yeah. So okay, so there is actually it's a very good question, because the answer is there are different categories in which you should view this. It's just that I'm very limited, and I can only do this in the category of C-star algebras, which is like compact quantum spaces. And this is why I don't see other Podlesh spheres as quotients. Piotr has experience in much more algebraic approaches, which are just slightly different. And then these Podlesh spheres are, they are all, for example, non-isomorphic for different Qs. For me, the C-star algebras are always isomorphic for different Qs, except for the one Q here. So, okay, there is a whole family, and this quotient one is a special like endpoint of the continuous family.
Okay, but this is some sort of regularity condition, but what I have in mind is like something like a space with an action of a quantum group, yes? Something like a G space.
Well, yeah. Yes, obviously. I mean, you can look at the quantum sphere as just stated without the action, but of course the action is an additional structure and it enriches the theory, but they are objects of the category of compact quantum spaces in general. So you can just study them. They're just not very interesting then. As you said, they're either unitization of the compacts or something slightly different, a little different, but not far from the compacts. Yeah, that's all.
May I just comment on this? And it is true indeed that you have to go beyond star homomorphism to have these other quotients, but everything is still sister of
Yeah, that sort of blows my mind. I can't understand.
I'm still given by but if you are really keen on having these sort of obvious quotients, then you just have to take a different sphere and it's
Oh, yeah.
quantum spheres and
But then you give up actions.
I mean, it's not going to be space because the other spheres, the other please are not full.
Yeah, there are many quantum spheres of different kinds and dimensions. There is a paper called The Garden of Quantum Spheres.
Anybody else?
Oh, yeah. Yeah, so I want to ask, well, we have, for the case of compact spaces, corresponds with, the Gelfand spectrum of the system. So, and the Gelfand spectrum can be thought of as a set of irreducible representations of the algebra, that's what we started with. And I want to ask, does it happen in the case of quantum compact spaces? Are they in some sense related to the irreducible representations of the algebra, or is it a completely different object?
Well, it's a completely different object, but there is some relation. For example, the irreducible representations of SUQ2 of this algebra. There is what? This is a circle and a point. So the circle is actually this circle, okay? But otherwise it's not a sphere. This looks like a free sphere, right? So it's, yeah, it's not. No, I can. In this case, actually, no. In this case, I think this is just an isolated point. This is yeah. It's this is just a primitive spectrum. It's not anything. I mean, it's not supposed to tell you what this C-star algebra is. It's yeah, it's just a shadow of this algebra. It's not. I don't think. I think it's an isolated. I don't remember it. I should actually. No, the infinite dimensional. Well, like the pi that I gave. So it's not exactly this one because this one's not irreducible, but it's very close to that. That's this one, and these ones are one dimensional. There is a circle of one dimensional representation, and then this is exactly corresponds to this picture here.
So Santiago is going to see a circle. Think about three sphere, taking the solid torus, and then you shrink the two torus boundary of the solid torus to a circle. That three sphere. And that circle is exactly the circle. But what everything else is inside the circle. That's a quantum point. Okay.
Yeah. I think we are over time for the break.
Yeah.
I'm sorry.
It's getting cold, but there is still some questions. Adam, distribute.
I have a question about the word quantum. Does it have anything common with something like quantum calculus? Because this Q would suggest that it's somehow similar.
Well, I mean, if by quantum calculus you mean the things that Alain Kahn proposed as his non-commutative geometry and things like this, then yes, clearly. As far as the name quantum groups, well, originally, and algebraic version of these objects was somehow used as describing symmetries of some physical models. Personally, I'm not a fan of this. I know of just one paper, which out of thousands, which has some merit in my opinion, as far as quantum mechanics and this stuff are supposed to work together. But the techniques that we use are very, very similar to a lot of things you do in quantum physics. Really, it's perhaps it's a coincidence. Maybe it's just that, you know, the theory of operators on Hilbert spaces is the most important part of mathematics, perhaps. But
So, sorry, I had in mind, like, quantum calculus is when you redefine derivative.
as a commutator with some like Dirac operator or something like this. Yeah, that's there is this, yes, this is the so-called theory of spectral triples. And there are spectral triples on SUQ2, spectral triples on quantum spheres, spectral triples on orbits. Yes, so the answer is yes.
I have a quick question about the question of like, what is the answer? Have you found any interesting symmetries by tweaking the existing like SU2?
Oh, of physical models, no? Well, there is a paper by Podlesh. It's called Quantum Mechanics of Two Particles on a Quantum Sphere. That's there. But this is like a technical thing. If you have two particles on a sphere, you can ask that they are interacting, and then you can quantize this story. But interactions are difficult in quantum mechanics. Basically, this is the whole point. So what you can do is quantize two free particles, but make the sphere quantum. And when the symmetries of the quantum sphere are the quantum SU2, the Hamiltonian for the free for two particles which are supposed to be free, but you make it symmetric under quantum group symmetry. It's different. It's different than just a sum of Hamiltonians for two non-interacting particles. So somehow it's like you're getting because you quantize the space and the symmetry group, you get some energy of the interaction. That's yes. Yes.
Perfect question. Anybody from the Zoom?
Okay.
Okay.
Is there a notion of homotopy group of quantum spheres? And are they as interesting?
Okay, homotopy theory. I mean, there are some papers that sort of go in this direction. I don't really know. In non-commutative world, all these cohomology theories and homology theories and things like that, they all come down to K theory. So I'm not an expert really. Piotr would know more. So I don't think there is a good theory of homotopy for this in this world. If you want some algebraic topology, you pretty much always end up with K theory, and this is well studied. Yeah, little k, yeah. Yeah, but not for C-star algebras. Somehow for C-star algebras, it's always trivial, right?
Like the round for
I think that there is a version well adapted.
yes, but it's topological.
Okay, I'm not a geometer.
Yeah, but we actually getting too far away, so let's.
Is there maybe, could you give some reason why for the stream of the symmetric group for n greater than 4 greater or equal, why this algebra becomes dimensional?
Well, the reason is I can easily construct an infinite dimensional image. So basically you have certain generators and some relations, and you wonder, well, can I realize this in some concrete way? Well, I can find a 4x4 matrix of elements which don't commute but satisfy that every row has a sum 1, every column has a sum 1, and every element is a projection. If I can find such a matrix of projections, that means that the universal algebra will not be commutative. Okay, because it has a non-commutative image by definition. Okay, any image I find, it has to be an image of this universal algebra. And also this image is infinite dimensional, so the universal algebra will also be infinite dimensional. And the image is what? P1 minus P1 minus Q, 0, 0, and the same matrix here as here, where P and Q are two projections in so-called general position in Hilbert space. So basically two projections that don't satisfy any relation, and you can construct these.
It looks like free product.
Yeah, it's actually it's a free product of two-dimensional.
So there's not enough conditions in the.
Exactly.
Yeah.
You could rephrase the question, why is it commutative for n plus 3? That's the kind of fun to compute. Okay, anybody from Zoom? Anybody
But it's
from
way
Zoom?
too late. I mean, someone
Don't
else.
worry. You can always reheat the copy. I see nobody from the Zoom, nobody from the room. So let me end with, if you can, however briefly, elaborate on what are precisely the mathematical conditions under which the formation of SE2 is unique, and what exactly did you have in mind for these higher dimensions?
So, okay, so you can deform the, what is it? So there is, okay, I will refer to the paper of Voronovich, which is kind of a cop-out, but okay, he defines a whole family of deformations. And the deformation parameter is a sort of multi-matrix with possibly many parameters, like, and then he looks at the representation theory of what you get, this quantum group. And this is
a quantum group, no?
Yeah. So he defines the deformation of a C-star algebra so that you still have a formal multiplication, and then if you ask that the representation theory of that quantum group that you get is like for SUN, so basically the reducible representations are indexed by Young diagrams and so on, then you can only do it in one way, with the special multi-matrix which only wanted one Q somewhere.
Like you don't care about it because many.
Oh yes, and I think Anna Kula did some.
Okay, so I think it's the highest time to thank us. Thank you.
I apologize for going over time.
And you stop recording.